Hello everyone. So this is a question from JEE Mains 2026 8th April Shift 2. Number of paramagnetic complexes among the following is. So we have a list of complexes or coordination compounds, and we have to tell the number of paramagnetic complexes among them, and the chapters involved is coordination compounds. Okay. So let's start with MnBr4 2 minus. So let's say the oxidation number of Mn is x. So therefore x plus 4 into the charge on Br is minus 1. So that will be equal to minus 2. So therefore x is going to be plus 2. We know that the configuration of manganese is 3d5 4s2. So therefore the configuration of manganese plus 2 is going to be 3d5. Okay. And the ligand, that is Br minus, is a weak field ligand. Therefore it cannot cause pairing of electrons. So therefore MnBr4 2 minus, that is this guy, will have 5 unpaired electrons, which can be represented in this fashion. So 1 2 3 4 5. Okay, so therefore it is paramagnetic. Cool. Then we have the second one, that is NiCl4 2 minus. Okay, so x plus 4 into charge on Cl is minus 1. That will be equal to minus 2. So x is going to be plus 2, and we know that the configuration of nickel is 3d8 4s2. So therefore the configuration of nickel plus 2 is going to be 3d8. Okay, and the ligand is Cl minus, which is a weak field ligand. So therefore it also cannot cause pairing of electrons. So therefore 3d8 will look something like this. Okay, so therefore you can see there are two unpaired electrons. So therefore this is also paramagnetic. Cool. Then we have the third one, that is NiCN4 2 minus. Okay, so x plus 4 into charge on Cn is minus 1, so it will be minus 2. So therefore x is going to be plus 2. Okay, and we know the configuration of nickel, that is 3d8 4s2. So therefore the configuration of nickel plus 2 is going to be 3d8. Okay, here the ligand is Cn minus, which is a strong field ligand. Okay, so therefore it can cause pairing of electrons. So therefore after pairing, initially they will look something like this before pairing. 1 2 3 4 5 6 7 8. So these two electrons will pair up. Okay, and after pairing they will look something like this. 1 2 3 4 5 6 7 8. Okay, so you can see there are 0 unpaired electrons, or all of them are paired, so therefore it is diamagnetic. Cool. Then the next one we have is NiCO4. Okay, so the charge of CO is 0, so therefore x plus 4 into 0 is going to be 0. So therefore x is equal to 0. So nickel is in the 0 oxidation state, so therefore the configuration of nickel will be 3d8 4s2 itself. Okay, so I can draw it in this fashion. 1 2 3 4 6 7 8, and 4s will also have 2 electrons, and 4p will have none. Okay, so electrons from 4s, that is these guys, are shifted to 3d. So one is shifted here, the other one is shifted here, so that we can have one 4s, that is this, and 3 4p, that is these three orbitals, vacant for sp3 hybridization. NiCO4 complex undergoes sp3 hybridization. Okay, so therefore these electrons are shifted. So after that, it will look something like this. 1 2 3 4 5 6 7 8 9 10. Okay, so this is 3D, then we will have 4s, then we will have 4p. So you can see there is one 4s orbital and there are three 4p orbitals for, and they undergo sp3 hybridization. And in 3D there are zero unpaired electrons, all of them are paired, so therefore this guy is diamagnetic. Next we will talk about the fifth one, that is COF6 3 minus. Okay, so x plus 6 into charge on F is -1, so it will be equal to -3, so x is equal to +3. Okay, so we know the configuration of cobalt is 3d7 4s2, so therefore the configuration of cobalt plus 3 will be remove 3 electrons, 2 from here and 1 from here, so 3d6, and the ligand is F minus, and it's a weak field ligand, so therefore it cannot cause pairing of electrons. So 3d6 will look something like this: 1 2 3 4 5 and 6. Okay, so therefore COF6 3 minus has 4 unpaired electrons, so therefore it is paramagnetic. Cool. Then the sixth one is FeCN6 4 minus. Okay, so x plus 6 into charge on Cn is -1 will be equal to -4, so therefore x is going to be +2. Configuration of Fe is 3d6 4s2, so configuration of Fe plus 2 is going to be 3d6. Okay, so and also the ligand is Cn minus, which is a strong field ligand, so therefore this guy can cause pairing of electrons. So 3d6 normally looks like this: 1 2 3 4 5 6 before pairing, and because of the presence of Cn minus, these 4 electrons will undergo pairing. Okay, so you can say they pair up. So these guys pair up, and after pairing they will look something like this: 1 2 3 4 5 6. Okay, so therefore you can see there are 0 unpaired electrons, all of them are paired, so therefore it is diamagnetic. Cool. Then the seventh one is MnCN6 3 minus. Okay, till now we have seen in all the complexes with a strong field ligand, they are diamagnetic. Okay, but you should not generalize this, because in this case you will understand. Okay, so again x plus 6 into -1, charge on Cn is -1, will be equal to -3, so x will be obviously +3. So Mn is going to be, configuration of Mn is 3d5 4s2, so configuration of Mn plus 3 is going to be 3d4. Okay, and the ligand is Cn minus, which is a strong field ligand, so therefore it can cause pairing of electrons. Okay, so 3d4, 1 2 3 4, so without pairing it will look something like this. Okay, and after pairing these two electrons pair up. Okay, so after pairing the situation will be something like this. So we will have this in the 3D and 4s and 4p. Okay, see, only see, one more thing is all 4 of them did not pair up. Okay, only 2 paired up and 2 are still half filled. Okay, so this is because this guy MnCN6 3 minus undergoes D2sp3 hybridization. Okay, so therefore only 2 of available 4 electrons, only out of these 4 only 2 pair up. Okay, so that 2 orbitals from 3D, 1 4s and 3 4p vacant orbitals are available for D2sp3 hybridization. Okay, so you can see here these guys, they undergo mixing to give us 1 2 3 4 5 6 D2sp3 hybrid orbitals, or you can say they undergo D2sp3 hybridization. Okay, so therefore MnCN6 3 minus, that is this guy, has two unpaired electrons. These are the two unpaired electrons. So therefore it is paramagnetic. Okay. So therefore be careful. Okay. It is not true that in all the complexes with a strong field ligand, they are going to be diamagnetic. They can be paramagnetic also. Okay. Okay. The next one is TiCN6 3 minus. Okay. So x plus 6 into charge on Cn is -1 will be equal to -3. So x is going to be +3. We know the configuration of titanium, that is 3d2 4s2. The configuration of titanium plus 3 is going to be 3d1. So it does not matter whether the ligand is, strong field or weak field, because there is only one electron, only one 3d electron, which can be represented like this. So it has, one unpaired electron. So therefore it is paramagnetic. And the next one is, the ninth one is, we have CuH2O 6 2 plus. Okay. So x plus 6 into charge on H2O is 0. That is going to be +2. So therefore x is +2. Okay. The configuration of copper is 3d10 4s1. So copper +2 configuration will be 3d9. Okay. So again, it does not matter whether the ligand is strong field or weak field, because there are 9 3d electrons. Okay. So to represent this, 1 2 3 4, so 1 2 3 4 5 6 7 8 9. Okay. So it has one unpaired electron, so therefore it is paramagnetic. Okay. And the 10th one is COC2O4 thrice 3 minus. Okay. So here the ligand is C2O4, which is, the oxalate ligand. COO minus, COO minus. So it has got a charge of -2. Okay. So therefore, x plus 3 into -2 is going to be -3. So x is going to be +3. Okay. So we know that the configuration of cobalt is 3d7 4s2. So the configuration of cobalt +3 will be 3d6. Okay. Cool. And in the spectrochemical series, you will have, roughly I minus, Br minus, S minus 2, SCN minus, Cl minus, F minus, OH minus, C2O4 minus 2, O2 minus, H2O, NCS minus, then NH3, En, NO2 minus, Cn minus, Co. Okay. So, this is Co and this is I minus. So this is the ligand which produces the strongest field. This is the ligand which produces the weakest field. Okay. So C2O4 minus 2, it's somewhere in the middle, and there might be, confusion regarding whether to take it as, as a strong field ligand or as a weak field ligand. Okay. But the catch is, whether a complex is high spin or low spin, apart from the ligand strength, the oxidation state of the metal is also very important. Okay. So oxidation of metal, in our case it is +3 of cobalt, very important in determining whether a complex is high spin or low spin. Okay. So high oxidation state, that is +3 or more. High oxidation state +3 or more. Okay. So these metals, so those metals which have, oxidation state of +3 or more than that, they favor low spin. Okay. Or you can say they favor pairing. Okay. So that's because higher metal oxidation state, since the oxidation state is very high, so the electrostatic attraction is high with the ligands. Okay. Therefore, there will be more repulsions between electrons of ligands and the d orbitals. Okay, so I will write that point. So high oxidation state increases electrostatic attractions with ligands. So therefore there will be more repulsions between ligands and d orbitals. Okay, so if I draw a rough diagram, let's say this is my central metal atom, let's say this is the z axis, let's say this is my y axis, and let's say this is my x axis. So therefore, ligands will be approaching the central metal atom through these axes. So if the oxidation state of the central metal atom is high, so they are attracted more towards the central metal atom. Okay, and because of these attractions, the repulsion between them is going to be more. Okay, and because of these repulsions, it results in a larger crystal field splitting energy, very important. Okay, due to high repulsions, so there is a large crystal field splitting energy. Okay, crystal field splitting energy is the difference between Eg and T2G. Okay, so the gap between T2G and Eg is very high. Okay, so because of this high crystal field splitting energy compared to pairing energy, therefore electrons prefer to pair, or you can say simultaneously pairing, or eventually pairing occurs. Okay, because of high delta, pairing occurs. Okay, so therefore C2O42 minus, that is the oxalate ligand, is not a very strong field ligand because it is somewhere in the middle, you can see. Okay, but still it causes pairing, or still pairing happens due to the high oxidation state of cobalt. Okay, because of the +3 state of cobalt, still pairing is going to happen. Okay, so in cobalt +3, the configuration is 3d6. So 3d6, will without pairing will look something like this: 1 2 3 4 5 6. And because of its very high oxidation state and high repulsions, therefore the delta is going to be very high. So therefore pairing happens eventually. So therefore these four guys will pair up. So therefore it will, after pairing, it will look something like this: 1 2 3 4 5 6. Okay, so therefore you can see it has zero unpaired electrons, all of them are paired. So therefore it is diamagnetic, very important. Okay, so a very similar question was, based on this concept, was asked in the JEE Mains 2026 28 January evening exam. So you can practice it. The link is in the description. Okay, so therefore the total number of paramagnetic complexes are, so I will circle them. First we have MnBr42 minus, that is this guy. Then we have NiCl42 minus, this guy. Then we have COF63 minus, that is this guy. Then we have MnCN63 minus, this guy. And then we have TiCN63 minus, this guy. And ultimately CuH2O6 2 plus, this guy. So there are total 1 2 3 4 5 6. So the answer is going to be 6 in total. Okay, thank you.